Hi everyone, so today we're going to be talking about how to separate stereoisomers, specifically discussing the process of resolution as well as racemic mixtures. So a racemic mixture is basically when you have a one-to-one ratio mixture of enantiomers, meaning that you have a mixture that is 50%, roughly 50% R and 50% S composition. And because enantiomers have the same physical properties, but they differ in their rotation of plane polarized light, the racemic mixture actually does not have optical activity, because if you imagine one component of the mixture rotates light in a clockwise direction, whereas one might rotate it in a counterclockwise direction, and those two kind of cancel each other out. And this leads to no optical activity of a racemic mixture. And a really famous example of a racemic mixture that caused a lot of problems was thalidomide. This was a racemic mixture that was used in drugs that were administered to pregnant women, and this led to a lot of birth defects. And the reason for this is because the drug contained a mixture of both R and S enantiomers, and only R was actually therapeutically active, whereas S was the one that was not only unhelpful but also led to a lot of the birth defects. And so this is a really infamous example and something to keep in mind when you're thinking about racemic mixtures and the importance of it in our everyday life. So resolution is basically the separation of enantiomers by first converting them into diastereomers. And so here we have an R and an S being converted into a diastereomer. And if you recall, in a previous video, we talked about the properties of enantiomers and diastereomers. So you'll find that in an achiral environment, enantiomers have the same chemical and physical properties except for the rotation of plane polarized light, whereas diastereomers have different properties. And this is really good, especially when it comes to resolution, because by converting these enantiomers into diastereomers, which have these different properties, we can use things like boiling points, solubilities, melting points, stuff like that, and use basic methods like chromatography and crystallography to separate these diastereomers, and then eventually through that process we will be able to separate enantiomers. And so the three major steps to know for resolution are listed below here. So you first start by reacting enantiomers with an enantiomerically pure chiral agent. So this just basically means you're reacting it with a molecule that has either, it has a stereocenter with 4 different things attached to it, or it has something that's not carbon that has 3 different things attached to it. So you want a chiral molecule, and we know what chirality means and what that looks like. After that, you separate the diastereomers that are formed, and then you regenerate the enantiomers by reversing the diastereomer formation. So in this case, our chiral agent is S-brucine, and you can see how it's chiral due to these like stereocenters here. You can kind of go through and identify all of them. We don't have to do that today, but that's what a chiral agent is. So to break it down a little bit more, let's say we start with a flask, just one flask, that contains both the R and the S forms of whatever molecule we're looking at. And after that, we add S-amine into this flask. And this here is our chiral agent that we add in. And now this S-amine reacts with the different components, the different R and S components of the racemic mixture. So we have an R acid with an S-amine and the S acid with the S-amine. Then we separate these diastereomers. So now we have 2 flasks, one with the R and one with the S. And you can protonate it with something like H3O+, which is where the acidification comes from. And this is how you regenerate the enantiomers once again. So here we have the R acid and the S acid, which is the same as what we started with, except now they're in 2 separate flasks. And that's pretty much the gist of what you need to know and understand for resolution.